Hi, and welcome to topic 4. This section is about inverse variation and the reciprocal function, 4-1. The essential question that we'll be looking at this section is how are inverse variation and reciprocal functions related and represented? Hopefully by the end of the section you can use inverse variation and graph translations of the reciprocal function. And I'm kind of excited because we've done so much with transformations that I think you're not going to have too much trouble moving that parent function around. So the first part, the model and discuss this time, it's on page 91 of your student companion. And
the two rectangles shown both have an area of 144 square units. Part A. Use the pen tool to sketch as many other rectangles as you can that have the same area.
So most of us have completed an exercise like this before. We're looking at length times width. And instead of using the pen tool, you probably just would write this in your workbook. But is there other ways that you could end up with a product of 144?
So I think about factors of 144, and so I thought, well, I could have this really, really long, skinny rectangle that would be like 1 by 144.
12 by 12 would be another.
Well, I like to go in an organized manner, so 3 by 72, and then, you know, we've got
2 by 72?
2 by 72, so it's a little fatter, but it's this one right there. And then we've got 3 by 48. We've got 4 by, I'm using my cheat sheet, 36. And so I'm thinking about what two numbers multiply together to give me 144, because I know that area equals length times width. What I notice, and maybe I could continue these sketches out, or maybe you've done this quite a few times in your past, is that as our width increases, our length is decreasing. I could keep going here. 6 by 24, 8 by 18, 9 by 16. That's one that a lot of people are going to miss. And then that 12 by 12. So,
how did you get that second number every time?
Oh,
what? Like I knew I wanted 144 for the area. Once you said 4 for the length, how did you get the 36?
144 is the area. If 4 is the length, then I'm wondering what the width is. So I'm going to go ahead and just divide by 4. Divide by 4. And
so in general, every time you were taking the area divided by the length that you chose?
Exactly.
144 divided by x. So I might even be able to graph something like that.
So like area divided by the length gave me the width, and in turn area
the 144 was the area, so that was set.
Yep. So here's our 144, and that was a fixed area. And then dividing by the length would give me the repeat, same thing. If I divided by the width though, I would get the length.
So if one goes up, the other goes down.
Easy.
That's a trademark of the inverse functions we're talking about.
And I think we've answered pretty solidly B. Always looking at our habit of mind, we're thinking, how does the formula for the area of a rectangle make sense with the relationship we found? Do you need to go back, time hop a couple? Use your pen. Because you should be able to answer that based on what we talked about so far. Identifying inverse variation. So when does it occur? If we're given a table, how can we check and see that it's an inverse variation relationship?
So the first thing you got to identify is what is inverse variation. And for most of us, at least this year, that should be very familiar to you from courses you've seen before. But inverse variation, just to be clear, is a relationship between two variables such that as one increases, the other decreases proportionally is the important word there. So just a downhill line is not necessarily inverse variation. It's got to decrease proportionally. So with a fix, you've seen it maybe with a K value.
Yeah.
For the table to represent an inverse function, the product of x and y must be constant. So 1 times 12, 2 times 6, 3 times 4, 4 times 3, the product is staying the same.
And I appreciate how they added a row to their table where they did x times y, and they found that that product was that constant 12.
So this is, if you ever see, does this represent inverse relationship? Check to see, does x times y give you the same number? And so then they're going to rearrange. Is that all the down it went?
Yep. Be sure to check the products for every pair of values before drawing your conclusion. So, thinking about it here in part B of the example, we're thinking of doing another example. And this one, sometimes counter examples are very powerful in math. And so this one we're looking at, and they're showing very clearly that 1 times 20 is 20, 2 times 17 is 34, 3 times 14 is 42. And so we would conclude that this is not an inverse variation relationship.
And this happens to be a downhill linear relationship, like I just mentioned, because kids get mixed up a lot. Oh, as one gets bigger, so as the x's are getting bigger, the y's are getting smaller. I thought that's what you said what it was. But nope, it has to be the proportional relationship, which is getting to this product piece. So multiplying them has to equal the same thing. So this is not inverse variation, this is linear.
All right, I believe we're on to the try it. So you're going to be around page 92, and we're looking at the top of 92, and we're thinking about determining. And so I love, again, how they gave us this table space where we can write x times y, and we can check whether that product is the same for every value they've given.
Great. I have a feeling you won't have much trouble with example 1. It's a nice little recap, though, of what you've seen before. So here for your notes, just to be super clear, when a relationship between x and y is an inverse relation, we say that x varies inversely as y. There's a couple different ways to say it. But inverse variation is modeled by this y over k to the x. So in our area example, 144 would have been our k, our constant. We call it a constant of variation. In other words, it's that product. 144 would equal x times y. So you know that third column that you got, k, is going to be found by multiplying x times y. Notice on these basic ones, there's not any adding or subtracting with it. It's just that fraction and just that variable, just keeping it super simple. The variable represents the constant variation. In this table, it's 24 because every time x times y equals 24. Pink.
So in order to use inverse variation, we need to kind of talk about it conceptually. So in an inverse variation where x is 10 and y is 3, we need to write an equation to represent the inverse variation and then find a different x value. So the first thing that we need to do is start with our kind of generic formula. Like start with y equals k over x, and that way you can plug things in appropriately. They're telling us right away that y is 3, so they plug that in. They're telling us that x is 10, so we plug that in. When we solve for k, we're going to multiply both sides by 10, and we find our constant. I don't like that being purple, I'm sorry. So once we get that, we can rewrite it, and now we have a formula that we can work off of, or an equation that we can work off of, and substitute in -6 and solve for our y.
So basically the x and the y you get at the beginning, establish your k value, and then you use the formula, that generic format with the k filled in to find your other ones.
And just to recap there. Remember to keep track of any negative signs, huge big flashing lights right here, when substituting into equations and performing calculations.
These are our triads already.
These are our triads already. So,
Okay.
yeah. So we want to think about that. K over x equals y. and then plug in what we know, and then solve for what we don't know.
So step one, to write the generic inverse variation formula. Step two, solve for K. Step three, rewrite with K filled in. So in this case, I would say figure out what K is and then solve for K and then rewrite it with K in there and solve for your other variable. So what is the equation that represents the inverse variation? So they've broken that down and now put K in, put X in as 15 with the K you found and solve for Y.
Moving right along into example 3. So again, we're using it when where would we ever use this in real life? And so on a guitar, the string length S varies inversely with the frequency F of its vibration. I've heard of some math teachers locally here in the building actually playing around with this relationship and testing it with something that measures the frequency.
Oh, interesting. Yeah. Okay, so on a guitar string, the length S varies inversely with the frequency F. So where does the S go and where does the F go? So as soon as you see varies inversely, you bring up this generic thing, and then they're going to help us fill this in. So write that equation out. Then it said, how is it? S varies, I don't want to say it wrong. S varies inversely with F. So S goes here. It's the one.
Now, Mrs. Conway, would this matter
Varies.
dramatically if they switched F and S?
No, actually, not when it's just in the standard, generic, unaltered way. We're going to end up transforming eventually. So I think it probably would be good to kind of stick with that format. But you're right. If you switch them, it would equal each other. And then the F varies inversely with, so basically it's usually going to be the one they say first, that's the lower. Y varies inversely with X, S varies inversely with F.
I love that we're starting here with the orange because that's where our anchor is. Then, like, this doesn't come out of random space, it comes right from here. And so it's not particular to this problem, it's that we've used this generic one and made it specific. So once we substitute in the values that they've given us, we can solve for F. Now, our very last step is always to kind of, what does that mean? And so the frequency of the 13-inch string is at 659.26 cycles per second.
So kind of ugly numbers, but that's how real life is when you use it.
And we're already at our, try it.
The amount of time, so T.
Well, first I want to start right here.
K,
Okay.
So Y varies inversely with X, and this says T varies inversely with air temperature, so maybe A for air. So time varies inversely with air temperature. And now we can plug in. You will probably always have to use your units. Keep an eye on your units here. At 20 degrees Celsius, the ice will melt in 20 minutes.
So I like to sometimes just identify time as T and air temp is A. Like I'll just make that note off to the side sometimes to keep that straight. That'll help me with units also. Alrighty. Onward. Now we get to graph. And so how do we graph this function? Well, as we start to think about it, we're saying 1 over x. So they're giving us kind of a fairly basic version. But the reciprocal function maps every non-zero real number to its reciprocal.
Why do they say non-zero, you think?
Oh, can you divide by 0?
Not.
So consider the domain and range. Here we see that domain with 0 excluded.
Remember, a domain is all possible x values. When we were in polynomials, we didn't really have to worry about that because all x values are fine in a polynomial. These are not polynomials. Once you have a negative exponent, so that's really what this, you could rewrite this as x to the negative 1. So this is not a polynomial, which means it probably does have some restriction, and the restriction is can't have 0 for x, or for the denominator, which is.
And when they call this the reciprocal function, well, is that an inverse variation relationship? And we want to make sure we're connecting those two things. So we've got our domain, everything except x equals 0. We've got our range, y cannot be 0 either.
Because if you have 1 over any number, there's no possible way to get an output of 0. So that means we have asymptotes, remember that word from before, a vertical asymptote at 0, and then a horizontal at x.
Where were we connecting
X.
asymptotes to? Would that be, that wouldn't be this year, that would have been a previous math course?
Oh, maybe. I was thinking we did a x can't equal.
I don't think
Maybe
we
we
have
didn't
done
try.
asymptotes yet, so we're gonna be coming to that.
Okay.
But there's some foreshadowing for the future.
Right? Sorry.
So when we graph, I love that we start at a table because a table is something very, very tangible that we can make. So when we plug in our value of -3, we get our y value or our f of x of negative, and I said -3 for x, so we get -1/3. And so
Just literally plot those points to see what this looks like.
when in doubt, plot it out and
I
graph
like
it.
this too because as x gets really, really, really big, you can kind of see why it's never gonna, the y values will never equal 0 because 1/3, 1/10, 1/100th, 1,000th, 1,000,000th, you're getting super close to 0, but not actually gonna touch 0.
And so here's our introduction to that word asymptote. And so when you're thinking about taking notes, this is going to come up a lot of times. The way you say it, asymptotes. And so just like Mrs. Conway was saying, as our x value increases, because of that denominator, as our denominator, I always think about it like sharing pie. Now you're sharing with 10,000 people, and so your slice is so little,
But you still have some,
but you
not actually
you get a
0.
taste.
And then same thing as you go to the negative side, it'll be a negative real small number, but it will be a small number. So this is kind of related to that idea of end behavior that we were working on. We were working on that in this book. So yeah, so as you go out, out, out to the far big or far small x values, what's your y values doing?
And that's our approaches, that language that we're connecting back to. And I think that's it. So the line, the graph will never touch the line x equals 0, and so it is called a vertical up and down asymptote. All right, I feel comfortable with
Something
this.
interesting that I always think it's a little x, if you have x can't equal a number, that's a vertical asymptote. It will never get touched. Vertical asymptotes never get touched. But horizontal asymptotes actually just describe the end behaviors. So sometimes weird stuff happens in the middle of a graph, and then we still would say it has a horizontal asymptote because the graphs, the y values are approached way out on the edges. So that's interesting. It's like some people think asymptotes are untouchable, but they do get touched within the horizontals sometimes. For an equation such as this one that does not involve very many parameters, graphing by hand does make sense. As you encounter a more complex one, you might need to use Desmos.
Or your TI-84. Still a handy tool. So this one, we have our constant, our k value would be 10. What are the domain, range, asymptote, and asymptote of the function?
So I think we've talked about domain and range a lot. And then how do you write asymptotes? So you really just like literally would say horizontal asymptote. Sometimes we just abbreviate it like that. And what, as x goes to infinity, what's the y values getting really, really close to? The y values are getting close to 0. So as x's go out, 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 the y values are getting close and close and close to 0. As x goes out and out and out, and sometimes there's 2 horizontal asymptotes a graph could have. Probably not this year, but it happens. And then vertical asymptotes, you'd say x, sometimes people will say can't equal, x can't equal 0. And why? Because you can't put 0 in the bottom of that.
All right.
Drag that point real quick. Let's just see what happens.
Which,
Yeah, the middle one. No, that's not true. It says drag the gray point. Oh, then this is leading to transformation.
foreshadowing.
And then this is the end of example 3. Should we be done for this video?
I believe this is the end of example 4.
Oh, should we just keep going?
Yes.
I think there's only example 5 next. That's it.
Graph transformation. So just like we just moved that around, now we're thinking about where those asymptotes and how that domain and range are going to change when we add something, when we subtract something.
So we start with the graph of the parent function, and I know that's still a little bit confusing for people, but this is a new parent function to this course. Like I said, you may have seen it in another course, but I always kind of think of 0, 0 as like it's not a point on the graph. In fact, it's not allowed. But I always think of it as kind of a home base mover, kind of like when I did a parabola, 0, 0 was a mover, left, right, up, down, or an x to the third, that 0, 0 point was kind of home base. So I think of home base as at 0, 0. And then it's asking us, okay, what's the x minus 3 do? Well, think of it like in parentheses, just like, I don't know if you can see this poster down here, just like we've been doing in all the sections, we have that, let me just write it. What was it? A, and then it had F, and it had B, X minus H, and then plus the K. And so this still is the same thing, except like X minus H is in parentheses, now it's just in the denominator. So this is gonna move it left or right. And the the K is going to move it up or down, just like it always has been. And so for this one, x minus 3, sometimes people think it will move left, but you know better, it will move right, 1, 2, 3, and then up 2, 1, 2. So my asymptote, that's what this is where those two asymptotes were crossing. And so now, let me get a different color. My asymptote will be moved up 2 and over 3. And so that new graph just gets drawn, and it doesn't have to be perfect, just kind of that outline.
But there's no stretch, so it's going to stay a rigid transformation.
Right. Okay, I'm going to erase this stuff and see. I'm sure they do exactly the same thing as I just did. I get excited. So then we'll get 3 units to the right.
If you're looking at the graph, it's actually moving. That we haven't seen that in this textbook very often.
No, make it go again.
So again, we're looking at how to write the domain and range. When we're thinking about it, they're saying all the x values except 3, and they're saying all the y values here except 2. And
What
so
was this notation called? It was called something. Set notation.
Yeah.
This is just a
Set
way to
builder.
write it. Set builder notation, that's right.
And so we can see that with our blue and our green lines up here. When we think about the habit of mind, a translation of the reciprocal function has a vertical asymptote at 5. What is a possible equation for the function? So it's been shifted, that vertical asymptote has shifted. That means it's a horizontal shift. If you can see, we're going back and forth. So I'm thinking that H is where we're going to really be focused on that. And so play around on decimals. Put in that parent function of 1 over x. Start there. Go to a new line and say, okay, well, is it x minus 5 or is it x plus 5? Playing around
In
decimals.
parentheses in the denominator.
Oh, yes. So is it x plus 5 or is it 1? Because I don't want to give you the answer, but I do think that we've narrowed it down now and you can kind of use the reasoning that you worked on.
The or between them.
Or
Maybe it's one of those, but you can try it out. Yeah.
parent function. All right. So as we're thinking about this, we always want to make sense and persevere.
Not only are the points of the graph translated, but the asymptotes are translated as well. And I always think of the asymptotes as a guide. So like I draw those in first and then my function.
Oh, I do too, definitely. it makes it a little easier because then you're kind of basing your graph off of zero in that case. So again, I would go back to the generic formula here, x minus h plus k, and use that to help me. And then of course this is an applet, so you can play around with it and move it around.
And always you can open a new window and play around on Desmos also to check what you think is correct is correct.
Excellent job hanging with us. That's the end of our video for lesson 4-1, examining the reciprocal function and that inverse variation relationship. High five out there in cyberspace.